Welcome to another video by Phoenix Medical Lectures. Today we will be seeing the elementary and physiological optics. First we will see light. Okay. So as far as light is concerned, the visible portion of the electromagnetic radiation spectrum. The electromagnetic radiation spectrum is known as visible light. So first we'll see the electromagnetic radiation spectrum. Okay, so on this side we have UV and on the other side we have infrared. So UV and infrared. On the side that we have UV, it extends X-rays, gamma rays and cosmic rays. On the side we have IR, it extends to microwave and short and long radio waves. Okay, so this middle portion is of importance because this is where the visible part of light, the electromagnetic radiation spectrum, lies. So this would contain Vib G-or. So the white light is divided into 7 colors of the rainbow, which is violet, indigo, blue, green, yellow, orange and red. So this constitutes the visible portion of the electromagnetic radiation spectrum. So this is 400 to 700 nanometer wavelength. So the 400 to 700 nanometer wavelength is the visible portion of the electromagnetic radiation spectrum, which is known as the visible light. So this side and that side, the side where UV, X-ray, all of this lies is invisible because it is lesser than 400 nanometer. On the other side as well, where we have IR, radio waves, all of that is also invisible because it is greater than 700 nanometer. So only if it is between 400 to 700 nanometer, that would be visible to the eye. So light is a form of energy whose interaction with the retina gives the sensation of sight. Coming to the nature of light, so there are a lot of theories which have been put forth regarding the nature of light, but the most widely accepted theory would be the dual nature of light theory, which means that the nature of the light, it acts as has two different characteristics. So one is that it acts as a wave. Second, it acts as a particle as well. So we have the wave theory and the particle theory, and the dual nature suggests that these both coexist. So now we'll see the different parts of the eye and how much wavelength of the light that hits the each part that travels through it and how much it absorbs the light. So first we'll see about the cornea. So the cornea absorbs all the rays that hits upon it, which is lesser than 295 nanometer. So the rays which enter through the cornea, if it is lesser than 295 nanometers, then it would not reach the lens or the retina, so it would not be a part of the visible light. So this is about the cornea. Coming to the crystalline lens. So the lens absorbs all the rays that travel through it, which is lesser than 350 nanometer. Okay. If it is lesser than 350 nanometer, then those rays cannot go beyond the lens because it will be absorbed by the lens. So what happens is that there is a catch when a person is suffering from aphakia. If a person has aphakia, which means that there is an absence of the lens in the pupillary area. So what happens is that the lens is not present to absorb rays between 295 nanometer and 350 nanometer. So what happens is aphakic patients can actually see between 295 and 600 nanometer. So what happens is that the aphakic patients can actually see, they are actually more sensitive to visible light, and they can see a quarter more than the normal person can see, because due to the absence of the lens they can see the light rays which are between 295 nanometer and 350 nanometer as well, which the normal people with normal lens and normal cornea and no other defects in their eye cannot view. Next is that eye is very sensitive to yellow green light. So why is this? So when we take a graph where the visible spectrum of light is there, normally we if we take this end to be 395 and such wavelengths and the other side to be 700 and more than that, the center part of the visible spectrum of light, if this is a graph, the center part of the visible spectrum of light, this place will probably be 550 nanometer. So this 550 nanometer is where the yellow and green light will lie. So the eye is more sensitive to yellow and green light. So we already saw that light is of dual nature, which means it acts as a wave as well as a particle. So coming to the wave theory. So the wave theory states that light acts like a wave. So when a wave is considered, the important factor would be the wavelength. The wavelength of light determines whether it is visible or not to the eye. So what is the wavelength? As the light travels in a waveform, the distance between two symmetrical paths, so this two symmetrical paths, so if this and this, if we draw a line from here to here, this will be considered as the wavelength. So the wavelength of a light wave is defined as the distance between two symmetrical paths of the wave motion. The second important thing is the amplitude. So the amplitude of a light wave will be the maximum displacement of an imaginary particle on the wave from the baseline. So this is the baseline. So the maximum displacement will be somewhere here. So if we draw a line from here to here, so the maximum displacement will be somewhere here, and this distance is known as the amplitude. So now we will see a phenomenon known as total internal reflection. So what happens is that when a ray of light is traveling from a denser medium, an optically denser medium, to an optically rarer medium, the angle of incidence, so this yellow line is what is the angle of incidence. So this yellow line, if it is more than the critical angle which I have drawn here, if it crosses the critical angle, then it will be reflected back to the same media. So this is the phenomenon which is known as total internal reflection. So first we'll see what is the critical angle. So the critical angle is something which refers to the angle of incidence in the denser medium. So this is the denser medium and this is the rarer medium. So the critical angle is when the angle of incidence is from a denser medium, and when it hits the rarer medium, the corresponding angle of refraction in the rarer medium should be 90 degree. So what happens is that if this is the critical angle, the maximum, so this would be the maximum, this will actually be refracted to the 90 degree in the rarer medium. So this part is known as the critical angle. So what happens is that when in a denser medium, the angle of incidence is more than the, so this is the critical angle. If it becomes more than the critical angle, as in the case of this yellow line, what happens is that it comes back to the same medium. So this is known as total internal reflection. So next we'll see the phenomenon of the prism. So what happens is that when an object is viewed through a prism, so this is the eye and the object is placed here. So when the object is viewed through the eye, it is actually seen here. So what it means is that normally in a prism, the object which is viewed tends to be virtual, erect, and it is displaced towards the apex, which is very important as far as the prism is concerned, because only in prism the image is displaced towards the apex. Coming to the cardinal points of the eye. So in a schematic eye, if we see, there are a lot of cardinal points, which is two principal foci and then two principal points, two nodal points. So these are the cardinal points. But when there are two points for each of the cardinal point, it gets difficult. So what happens is that we have the reduced eye. In the reduced eye, it is easier to understand the optics. So what happens, the one single point from the two points that is present in the cardinal points is taken, and that particular point is kept as the principal point, as a nodal point and the focal point, and this is known as the reduced eye. So I have marked the focal point, the principal point, nodal point. So the principal point, the principal point lies 1.5 millimeter. 1.5 millimeter behind the cornea. So this is the principal point. The next one here is the nodal point, and this lies about 7.2 millimeter behind the cornea. 7.2 millimeter behind the cornea. Next is the focal, anterior focal point. So this anterior focal point lies 15.7 millimeter anterior to the cornea. 15 15.7 millimeter anterior to the cornea, and then we have the posterior focal point, which is here. This posterior focal point lies 24.4 millimeter behind the cornea. 24.4 millimeter behind the cornea. So these are the main cardinal points, and that is easily visualized when we see it in the form of a reduced eye where one point is taken instead of two. So the anterior focal length is 17.2 millimeter and the posterior focal length is 22.90 millimeter. So this anterior focal length is the distance between F1 and the cornea and the principal point. So the principal point in the cornea is about 1.5 millimeter, and the distance between the focal point, anterior focal point, and the cornea is 15.7 millimeter. So together it is 17.2 millimeter, whereas the posterior focal length is the distance between the cornea and the posterior focal point is 24.4 millimeter, and the distance between the principal point and the cornea is 1.5 millimeter. So when we subtract that, the distance between the principal point and the posterior focal point is 22.9 millimeter. So the total dioptric power of a reduced eye is plus 60. So this is very important. The dioptric power, total dioptric power is 60 diopters, plus 60 diopters. So this 60 is contributed, 43 diopters is contributed by the cornea and 17 diopters is contributed by the crystalline lens. So this is the reduced eye. Now we will see the axes of the eye. So first the black line. So this line is the visual axis. So the optical axis, sorry. So the optical axis is that which is the line that passes through the center of the cornea, lens, and reaches the retina on the nasal side of the fovea. So this is the line between the cornea, lens, and the retina. So this is the optical axis. The second one is the red line. This red line is the visual axis. This axis, so if we keep this as a fixation point, right? So if this is the fixation point, then from the fixation point to the fovea, so it passes through the nodal point in between. Like we saw in the previous one, this particular place was the nodal point. So from the fixation point to the nodal point, reaching the fovea is the visual axis. The third one is the yellow line, which is the fixation axis, and this is the line which joins again the fixation point with the center of rotation. I'll mention that, to the center of rotation. So these are the three axes. So there are four main angles of the eye. The first one is the angle alpha, which is here. So already, as I've mentioned, this line is the optic axis and this line is the visual axis. So the angle between the optic axis and the visual axis, this is the angle alpha. The second angle is the angle gamma. So this is formed between again the optic axis here and the fixation axis. So the yellow line is the fixation axis. So this angle is angle gamma. So the third angle is angle kappa, and it is formed between again the visual axis. The red line is the visual axis, which is between the fixation point, nodal point, and the fovea. So this visual axis and the central pupillary line. So the central pupillary line is something which lies perpendicular to the cornea at the center of the pupil. So this is the central pupillary line. So the angle between the central pupillary line and the visual axis is the angle kappa. Next is the visual angle. So this angle is when the eye is focused on any object, the angle between the object and the nodal point, which is subtended between the object and the nodal point, is known as the visual angle.